live session talk. Now, as usual, we will go according to the questions that you have asked, and we have categorized them according to the different topics. So let me go to the next slide. So the first few slides are about 2, 3, 4 trees and B trees. There are some questions about the insertion into a 2, 3, 4 tree. A few slides are mentioned, which I have chosen for illustration purposes. Now, if you, first thing is 2, 3, 4 tree has 3 types of nodes. It's called 2 node, 3 node, and 4 node, primarily depending on how many pointers are there associated with that particular node. For example, a 2 node has 2 pointers, therefore 1 data item. A 3 node has 3 pointers, left, middle, and right, and therefore it has 2 data values, key values or data values. And a 4 node has 3 data values and 4 pointers. Now, at the leaf node, understandably, these pointers are set to null. These links, left link, middle, two middle links or 1 middle link, and the right link. So the idea here is no node can have, other than the leaf nodes, these nodes are only these 3 categories, and they can have 2 pointers or 3 pointers or 4 pointers, right? So the beauty of this is it makes the tree balanced. I mean, if you insert these numbers like 10, 30, 60, 20, 50, 40, 70, whatever this sequence of numbers in a normal binary search tree, you may find out that the tree gets skewed. The tree will get skewed. If you really do that, you'll find out that the tree will get skewed. But the property of the 2, 3, 4 tree combined with the insertion deletion algorithms will never allow you to make a skewed tree. And therefore, there are certain properties which can be proved. One of them is categorically written in this slide, and it will be repeated in all the next slides, which is the fact that all leaf nodes will be in the same level, will be at the same level. Leaves are at the same level. We cannot have leaves at different levels. Now, how is it ensured? As I said, the insertion deletion algorithm will always make sure that this happens. Now, the slides that you have given to me, for example, I mean, you can try with any example and you will find out that if you use the insertion deletion algorithms provided to you, you cannot have leaf nodes at intermediate levels. They will always come at the same level, which is at the very bottom, the bottom level actually. Now, like for example, I insert 10, only one node, I mean, 1, 2 node will be created, 10, 10, 30, a 3 node will be created, 10, 30, 60, a 4 node will be created. Now, the moment you go for inserting 20, the idea is not that I will insert 20 in a already, I mean, where will it be? 10, 20, 30, 60? Not allowed. Why not allowed? Because I can only have 2 node, 3 node, and 4 node. Therefore, a 4 node cannot have more than 3 data values. So I cannot have 4 data values in a particular node. Now, the moment I encounter a 4 node, I have to split it. And only after that, I will do the insertion. How do I split? It's also very simple. Split it at the middle. The left-hand side of that particular, I mean, earlier 4 node will become the left child, and the right-hand side of the middle will become its right child. So accordingly, I have 30 as the root, 10 at the left, and 60 at the right. And now you go for inserting 20. You can easily insert 20 in the 10 node, which will become something like 10, 20. So the left one. Now after that, if you go on inserting, for example, you insert 60. So 10, 30, 60, 20. 20 will be inserted to the left of 30. Then comes 50, right? So 50, the moment 50 50 will be inserted I mean, this step has not been shown. 50 will be inserted somewhere. I mean, let's say I've inserted up to 70, and the B tree looks like, as I have shown in the left B tree, it is like that. Now I want to insert what? I want to insert 80. So I decide from the root which way to go. It is beyond 50, so I have to go to the right child of the 30-50 node, which contains now 60 and 70. So this is a 3 node. I can insert easily one more value there. I insert 60, 70, 80. So up to this it is fine. Now I want to insert 15, for example. So 15, how do I insert? I go to the root node. Where do I need to traverse? Left of 30. I traverse to that node, left of 30. How many values does it contain? 2 values it contains, 10 and 20. So I insert 15 in that particular node, which is now 10, 15, and 20. Now after that, I insert, for example, I mean, let's say another. I mean, I have now inserted 15, and then I want to insert 90. Right? Yes, 90. Now, when I want to go for 90 insertion, then the moment I do that, what happens is I find out. I mean, I may find out 2 ways. I mean, I want to insert 90. So I go to the right of 50. The moment I go to the right of 50, which node do I encounter? I encounter a node which is already a 4 node. Now, the moment I encounter a 4 node, I need to split that particular node. So what it will become? It will become 60, 80, 60 on one side, 80 on the other side, 70 will go to the root of that. Now, therefore, the root will now contain 30, 50, and 70. And therefore, the root contained earlier 3 links. Now it will contain 4 links. To the left of 30, 10, 15, 20. Between 30 and 50, the link is 40. Between 50 and 70, the link is 60. And beyond 70, the link is 80. Now, do remember, every time I'm writing this, that on the way from root to the leaf, split a node, which is a 4 node that comes on the way. So till now, this was not so visible, but next step, it will become visible. So for example, I want to insert 100. Just I want to insert 100. Even if it is not 100, I wanted to insert anything. I encounter the root node, right? And what kind of node is it? It is a 4 node kind of a node. It's a 4 node. It has 3 values, 4 pointers. Therefore, it is a 4 node. The moment it is a 4 node, what I am inserting is immaterial. I need to split this node. I need to split this particular 4 node, which is 30, 50, 70. So which will go to the root now? 50 will go to the root. Which one is to the left of 50? 30. Which one is to the right of 50? 70. Now, which nodes out of these leaf nodes will go to 30? Left node of 30 originally plus whatever was the link between 30 and 50 will go as right link of 30. Similarly, what is the right node of 70? Originally, 70 has a right node to beyond 70. That particular link will be the right link of 70. And what is left link of 70? Whatever was the link pointing to, which was earlier between 50 and 70, that link will be the left link for 70. So whatever value I wanted to insert, be it 100, be it 9, be it 15, 16, whatever number I wanted to insert, I encounter a 4 node, I split it. That's my philosophy. After I do that, then from that point onward, I will traverse again. So is it that any node that exists in the 2, 3, 4 tree will be split, which are 4 nodes? No. On the way to insert in a particular node, a particular number, on that way, whatever 4 nodes come, I will definitely split it. Now, so therefore, after split, this is my new tree. And if you say how to insert 100, yes, I want to insert 100. It has to go to the right of 50. I come to 70. I have to go to right of 70 because it's 100. Then I go there and I find out 80, 90, 100. So I insert 100 in that particular node, which contains 80 and 90. Now, this is what it is. Now, the question, as I understood, probably is what is the magic by which the leaf nodes always come at the low level, at the lowest level? How do they come at the same level, which is the lowest level or highest level? I mean, that depends. At a particular level, leaf nodes do come. How is it possible? Now, exactly, that can be mathematically proven. I can prove it mathematically, but so that proof is not necessary. Only thing is, you understand that in a normal tree, in a binary search tree, I can have a node other than leaves, which has the left child and not the right child, or the right child, not the left child. Those are possibilities, right? Now, the way I defined my 2, 3, 4 tree, that is no longer a possibility. You have to be either a 2 node, in which case both your left child and right child should be there, or you have to be a 3 node, in which case your left, middle, and right child should be there, or you have to be a 4 node, in which case all non-null children are to be there. Now, only in the leaf nodes, your children may be null, maybe null. You cannot have any children. Whatever node you are, 2 node, 3 node, 4 node at the leaf, your children will necessarily be null. So this is a huge, deviation from the definition of binary search tree vis-a-vis a 2-3 tree or a 2-3-4 tree. I cannot have a node which has a left child but not a right child. I cannot have a node which has a right child but not a left child. Right? I cannot have them. At the leaf nodes, all these children are null. And at any intermediate node, you have to have, if you are a 2 node, you have to have both non-null children. If you are a 3 node, you have to have 3 non-null children. If you are a 4 node, you have to have 4 non-null children. So that's a must. So this restriction actually makes your tree balanced. And whenever a tree is balanced, it cannot be skewed. Right? So this deviation you try to understand, appreciate, and then you will find out that this is the key feature. This is the key feature in the definition of 2, 3, 4 tree, which makes this tree always balanced, and the leaves come at the very same level necessarily. Right? Now, insertion deletion algorithms are made in such a manner that these properties of a 2, 3, 4 tree is never violated. That's the answer to your question. Now, formally, mathematically, this can be proved. Right? Now, the question is, the next point that I understood is a 2, 3, 4 tree is generalizable. True. Now, 2, 3, 4 tree is like a binary search tree, is a data structure needed for, for primary memory. These are called primary memory data structures, where the data and these data structures are kept in the primary memory. They are not stored in the secondary memory. Now, in database management system, these data structures are actually made in the secondary memory only, right? So we need to have data structures which fit in external memory, which is secondary memory. And 2, 3, 4 tree, the definition of 2, 3, 4 tree is nothing but a special case of the definition of a B tree. Now, if you look at a 2, 3, 4 tree, as I said, any node which is not leaf node can be a node either of these 3 types, meaning it can have two links to 4 links and 1 data value to 3 data values. This is exactly written in the second and third points of the second bullet. Right? Now, all paths from the root to leaf are of the same length. This is not a definition. This is a property. You can prove it. This is a property. But the second bullet, sub-bullet, and the third sub-bullet in this, so second point and the third point in the second bullet are points in the definition. The special cases is also a point in the definition. If the root is not a leaf, it has at least 2 children. If the root is a leaf, it can have 0 to n-1 values, and no non-null. I mean, all children are null. When I say two children, I mean non-null children, non-null pointers. Children means non-null pointers. So you can do one thing. You can side by side put the definition of a 2, 3, 4 tree and a B tree, and you will be astonished to see that 2, 3, 4 tree is necessarily a special case of a B tree. Now, what's the difference between them? A B tree can be implemented in secondary data structure, secondary data store. I mean, secondary, I mean, your disk and things like that. So that's an external data structure. While 2, 3, 4 tree is necessarily meant for data structure in the primary memory. So it is internal data structure, right? So that is, I mean, so you can say that 2, 3, 4 tree is the precursor of B tree, which we use in our database management course, as well as in database implementation of the files in the database. I hope that I was clear in what I said. If you have further questions, you can always come back to me, and we'll be happy to give you further clarifications. So then someone told me that this insertion algorithm could not be understood. I mean, she or she could not understand it. So let me tell you, take this example and show you what this means. Now look at the B tree. I think you are aware of this B tree. I mean, so the structure of the B tree is understood to you. And assume that I am looking for creek, the record for creek. So first question, I go to the root, and my question is creek less than Mozart alphabetically? Yes, creek is less than Mozart. So creek is less than Mozart means I have to follow the left link of Mozart. I do that. So I come to the block for Calipari, Einstein, and Gold. Now my question is creek less than Calipari? No, it is more than Calipari. Now is it less than Einstein? Yes, it is less than Einstein. So that tells me that I need to go to the link for left link present in the left of Einstein. So I go to the link to the left of Einstein. Then I ask the same question: Is creek less than Calipari? No. Then is creek less than equal to less than equal to creek? Yes, it is less than equal to creek. Is it equal to creek? It's equal to creek. So I got it. Right now, for example, somebody asks me, I want to go for Srinivasan. I want to start Srinivasan is there or not. So I take Srinivasan and again start with Mozart. Is Srinivasan less than Mozart? Less than equal to Mozart? No, it is not. Then I find that I cannot ask this question anymore. So the moment I cannot ask this question anymore, what I need to do, I need to take the last. I need to look at the key value where I ask the question last. Where did I ask the question last? Mozart. So to the right of Mozart, what is the link? I need to traverse that. So to the right of the Mozart, the link points to a particular block. I go there. Now, is this Srinivasan less than equal to Srinivasan? Yes. The moment you say it is less than equal to Srinivasan, then the moment I say it is less than equal to Srinivasan, I need to traverse the link to the right of Srinivasan. Understand my point? If the question is my link, is my key less than equal to Srinivasan? The answer is yes. It is less than Srinivasan. If the answer is yes, I traverse the left link of Srinivasan. But if my key is equal to Srinivasan, then I have to traverse the right link of Srinivasan. Now, one may ask me, why don't I stop there? I got it. No, I didn't get it. I got the key value. I do not know where the data for that particular record is present. The record, I understand record is there, but where is the record? The record must be in a block. Where is the address of the block? So therefore, you need to go to the leaf. You have to go to the leaf. Now, when you go to the leaf, the Srinivasan has a left link, right? You see the left blank part that has a link. It's a non-null link. This link points to the space in secondary memory where the record for Srinivasan is obtained, can be obtained. Got my point? So these are not null. This is not null. This is not null. This is non-null. They point to the records for, I mean, this points to record for Brunt. This points to record for Adams. This point to record for Einstein. These are non-null links, right? So you understand that in a B tree, B plus tree, I have two types of links. These links in the intermediate level, they point to blocks for the other nodes in the B plus tree. But at the leaf node, these pointers are pointing to records. These are record pointers, right? So I hope now this idea is very clear. Now let me go to the indexing. Normally, many questions actually come from index. So I need to go to the index like dense index, sparse index, private index, cluster index, secondary index, and all that. Now we all know in a sparse index, the actual file is large, and the keys, the primary, the searchable search key, actually search key is stored, but all search keys are not stored in the index file. Like the search keys are 10, 20, 30, 40, and so on and so forth. But the sparse index file contains 10, 30, 50, 70, 20 is not present here, 40 is not present here. We assume that this 10 points to the beginning of a block. In this block, there are some records. Let's say every block contains 2 records. In this example, that is being shown. Every block contains 2 records. So if you ask me, where is the block for key 10, for search key 10, I go here. If you ask me, where is the block for search key 20, I check that the address can be obtained for 10. 10 is through this link, for 30 is through this link. Therefore, I need to go to the link which is pointed to by this particular link, and then I have to find out 20 sequentially. That's what I need to do. So this is sparse index. Now your question was about how, what is there if I want to insert? How do I do that? Now assume that here 20 was not there. Just assume, and you say that I want to insert a record whose search key is 20. Then nothing needs to change in the index file. Nothing needs to change in the index file. You have an empty, you have a block which has space, and the record can be easily inserted with the search key 20. The index file remains unchanged. But the example that is given here is a little more interesting. It says that I want to insert a record whose search key is 65. Now search key is 65 means I cannot store it in this particular block. This block is full, 50, 60. Now originally this block was 60, 70, 80. So 70, 80 was also full, no? So two ways I can do it. One is that in this block 70, 80, I shift 80 to a new block, and in 60, before 675, I do a 65, and then another block may be created as 80, 90, whatever. There is a problem though. The blocks need to be, these blocks are to be rewritten. Lots of blocks may be rewritten depending on where you are inserting this. Number one. Number two is you are inserting 65 at the top of the block, right? Therefore, this 65 has to go in the index file as well. And 70 is no longer the beginning of any block. 80 is that. So you have to put that there. So this index file also needs to be reorganized, rewritten from that point of time. So sometimes, therefore, what we do, we create a new block. We create a new block in which 65 is inserted, and the new block is chained with the block after which it is being stored. So what happens is the number of records that can be obtained from 50, is no longer one block, but it becomes more than one block. It becomes 2 blocks. But then this is much better, because in this case I do not need to reorganize the blocks of the file as well as blocks of the sparse index. So this is about insertion. If you want to delete, right? If you delete, let's say here you are deleting the row, the record number 60. So this block gets a new space, but nothing changes in the index file because you have not deleted 50, right? But next would be if I delete 50. If I delete 50, minor change, I understand that 60 will be available there, but my index file will never contain 50 anymore because 50 does not exist in my file anymore. It will be changed, altered by 60. That is what it will be, right? So this is how we insert, delete, and things like that we do, and each one has their cost. We do not need to calculate the cost, but each one needs a huge cost in terms of block transfer, block replacement, things like that. So that their costs. Now many questions have actually come because of the definitions of primary indexing, clustering indexing, and secondary indexing. Now, as far as Korth, or for that matter, the PPT that you have seen from Dr. Partha the same as Korth, they say that primary indexing and clustering indexing are almost the same thing, which is right. In both cases, the search key, the index key, has to be such a key, such a column on which the data is physically sorted. True. Now, the moment the index key or the search key on which the physically data is sorted becomes the primary key, that is usually called primary index. And this is also written in Korth as well as in Dr. Partha's slide. So do understand that there is a small difference between primary index and clustering index. In both, the data is physically sorted on the index key, no doubt about it. Only point is, if the key is a primary key, then we tend to call it a primary index. And if the key is a non-primary key, then we tend to call it a clustering index. After all, clustering has a sense, clustering has a meaning. And in the example, you'll find out why do I call primary and why do I call clustering. Now, secondary index is simply different. In this case, the search on which you are indexing is not the key on which the data is physically sorted. It is not sorted in that manner. So it is a costly key. It is a costly key. The moment you do this, it is a costly key. The differences wise, I told you, in primary index, the index key or the search key on which the data is sorted is the primary key, and therefore the key values do not repeat. But in cluster index, typically the key on which it is indexed or the key on which it is sorted is not a primary key, and therefore most often you will get duplicate values of the key, duplicate records you will find out with the same key value. And therefore, you need pointer for us. We'll find out. We'll have an example. Like for example, you see now this is a cluster index. One is not a primary key. Understood? Because so many ones are there, so many twos are there. This is not my primary key, but this is on which this is the key on which this is the column. This is the key on which physically the data is sorted. Right? So if I ask you, I want to go to a record with key 1, then you take me to this particular record, right? But now out of these 3, anyone would suffer. Someone will be needed by me. Not all of them will be needed by me. My query will need one of them, right? So this is the slight subtle difference between clustered index and the primary index. I hope I'm clear now. This point was not so categorically mentioned in the slide that Korth had or Dr. Das had. Now, in a secondary index, first of all, note that this is my index 1, 2, 3, 4, 5, 6, 7, 8, nicely sorted. But the key, the column for these values are not, the data is not sorted on this particular column or on this particular key. So 1 is obtained here, 2 is obtained here, 3 is obtained here. More problem is, I mean, this does not have a particular situation where I have 2 records in this file with value 1. Then there would be this one here and another one maybe somewhere here. And therefore, then you need to have 2 entries for this particular key 1, not 1 entry, 2 entries for this particular key 1. Right? Because it is not a primary key. It is not a key on which you can sort. It is not a primary key. There can be duplicates, and these duplicates are not necessarily contiguous. These duplicates are not on the same, not in the same place. So, for example, here if you look at, like, just look at this example. This 80,000. 80,000. See, there are 2 records for 80,000. One is here, and the other is here. 80,000 is here. This field. The point is, this is sorted. The data is actually sorted on this field, but I want an indexing on this field, which is not a key and maybe duplicate. Right? So therefore, this is called secondary indexing with bucket. 2-level secondary index, multi-level secondary indexing with bucket. Now, naturally, the question that was asked was a small file. Tables and files in these questions are the same thing. It's a file. We cannot have a secondary index. After all, it is time consuming. It is a very small file. Sparse index does not make sense, and I do not have duplicates, so clustering index is not the best thing. So it is a primary index. Basically, it's a dense index, right? I mean, sparse index and dense index are basically 2 parts, two types of ordered indices, which is primary or clustering, as you can say. Right. So that was about the assignment as well. Now, a very standard thing: serializability, conflict serializability, view serializability. Many people ask these questions. Now, this concept of serializability comes when you have concurrent transactions. If you do not have concurrent transactions running on in a particular database, then concept of serializability has no meaning. So first of all, you have concurrent transactions. The moment I have concurrent transactions, maybe 2 transactions are there, and both of them may like to work on a particular data item, maybe let's say X. Now maybe T1 writes X, T2 reads X, and things like that. Therefore, if they are free to do them in any way they like, then the problem becomes depending on how these transactions were scheduled ultimately, depending on that, the result outcome of that particular database will be dependent. And what is the problem then? The problem is that the transactions are run at different points of time, the same transactions on the same instance. The result of the resultant database will vary from one run to another run. Like, you have a program which works on a particular variable 20. In one run it becomes 30. In another run it becomes 40. Then your program is not so useful, because your program, for runs, you cannot tell that person who runs it what is the result that will be obtained after running your program. So therefore, we need to have a situation where a number of transactions which are concurrent can be made to be equivalent to some serial schedule, where these transactions are done one after another. Now, when we do this, there are 2 types of serializability which are important, which you look at. One is called conflict serializability, and the other one is called view serializability, which we'll talk one after another. Now, there are conflicting operations in a particular, among 2 transactions, and if these conflicts, are resolved, or the order of the conflicting operations are the same in those transactions, then we call it the transactions into schedule. So schedule has many transactions actually. Then we call it a. Let us take an example. I think there is an example. Example is a little far. So for example, you can look at this as well. You see, T1 this is one schedule with T1 T2. This is the second schedule with T1 T2. Now T1 writes a reads writes B, T2 also reads writes A and B. The question is, are they, I mean, will they give rise to, I mean, are there, they have conflicting operations. So T1 writes some data and after that T2 reads it. Now, whatever, I mean, way I schedule T1, T2, I have to obey this particular ordering. That after T1 writes this A, only then T2 can read this A, right? We cannot do it otherwise. Similarly, this read write, T2 has to read this A and then write this A. This ordering is important. And this ordering, these orderings are captured in a formal manner in these areas, conflicting instructions, right? Now assume that there are two transactions, two instructions in maybe in a transaction or in different transactions, where one of them is a read item, read, and the other one is, I mean, there are two instructions, and the basic instructions are either read or write. So there are going to be four possibilities. Li is read, Lj is read, Li is read, Lj is write, Li is write, Lj is read, Li is write, and Lj is write. Now, if both instructions read, then the ordering does not matter. But if one reads and other writes, then their ordering matters. The moment the ordering matters, I call it a conflicting operation, conflicting instruction. And also do understand that if I read B and another transaction reads A, there is no conflict in it. They have to read and write the same thing, same queue. The same queue, one has to read, the other has to write. Then this read has to precede this write has to precede this read if Li is a prior instruction. So this is what we want to do. So in a schedule, Li, Lj, if they are consecutive and they are conflicting, then the ordering of their conflict must be maintained. Otherwise, if they are not conflicting, I can interchange them easily in the schedule. We'll do that. Don't worry about that. So, for example, you see this read B and this read A. Are they conflicting? No. Why? Because this is on A and this is on B. What I can do, therefore, I can say read B comes here and read A comes here. This is called swapping. Read B and read A are non-conflicting operations. They can be swapped. What is meant by that? Can I take read B here and read A here? No. Take read B to the place where read A is present in the T1 schedule, in the T1 transaction, and take read A to the position of read B in T2 transaction. So I get this read B here and the read A here. Now this write B and write A, are they conflicting? No, not at all. They are not conflicting. So what I can do, I can swap them. Write B in place here and write A here. If I do that, I see I get read A, write A, read B, write B, read A, write B, read B, write B. So I see that to maintain the conflicts, to resolve these conflicts in a very nice manner, T1 has to be done first and then T2 has to be done. How did I achieve it? By swapping non-conflicting instructions in this transition. So schedule 2 is a conflict serial. I mean, schedule 2 is a serial order of the transactions. Since I could achieve it, schedule 1 was a conflict serializable. Now, question is, how can I check whether a schedule is conflict serializable or not? Then I have to draw up a precedence graph. Let us show that. Let us show this. Check. These are conflicting. And which has to be done first? T2 has to be done first and then T3. So I have a graph where T2 is a node, T3 is a node. And from T2, I draw an edge to T3, signifying T2 has to be done first because this R has to be done before this T3's W. In any serial, if I want to serialize the transactions in this schedule, there is no way T2 can be done later than T3 because T2's Rx has to be before T3's WX. Now comes WX and WX, T1 and T2. If you look at, this has to be done first and then this can be done. That means T2 to T1, there must be an edge. and then this Wx and then this Wx. Which one comes first? This one comes first. So T3 comes first, then an arrow, then T2. If I draw this diagram, I will get a cycle. Why? Simple cycle. T2 to T3, T3 to T2. You see, T2 to T3, then T3 to T2. A small cycle with two particular nodes. So this is a graph. What kind of a graph? A graph has nodes. What are the nodes? The transactions are the nodes. How am I drawing the arrows? I'm getting pairs of conflicting operations in these transactions. Wherever I get them, depending on which one happens first, the arrow comes out from that, and whichever is happening next, the arrow goes to that particular transaction. This is how I'm doing it. Now, if this graph has a cycle, that means this schedule, conflicts in this schedule cannot be resolved. I cannot resolve these conflicts, and it is not conflict serializable. And if there is no cycle, then naturally the conflict can be resolved. And what is that serial schedule? Do a topological sort of that graph. The moment you do a topological sort of the graph, you'll find out the conflict serial schedule as well. Now comes view serializability. Now, two schedules are view serializable if there are three conditions which are met. The first one is if a transaction T1 in a schedule has an array from the initial database, then in S2 T1 must have array from the initial database. That's initiality. Then final write. If T1 has a WA at the last in S1, then the same T1 has to have a WA at the very last in S2. And then update read. I mean, this is a little complex. Ti has array after WA. I mean, you update read. You update and then read. So some WA is done in S1, and after that array is done. If that happens in S1, then the similar thing has to be there in S2 as well. So you have to look at the schedules. Like for example, these are. I mean, this is the same thing I have said. You see that the data item is read first on R and then written onto by T3, right? So T2 to T3 there will be one particular arrow, and so I have T3 to T2 to T3 that you have. Now final update is done by T1, right? Final update is done by T1. So T3 or T2, all of them gives, I mean, there is an arrow between T2 to T1 and T3 to T1. For Y, there is no, actually there is no, restriction or no question of WWA is not there, is not a problem here. I mean, it can be done at any place. There is no restrictions on that. Now, so what we have here is this kind of a graph. Does it have a cycle? This is directed graph. It doesn't have a cycle. Since it doesn't have a cycle, I can say that this is view serializable. This is view serializable, but the same schedule was not conflict serializable. Now, what is the view serial order in this case? Again, as I said, what you can do a topological sort. What is a topological sort? Go to a node which does not have any incoming edge, T2, right? Then go to some edge which only depends on T2, So that is T3. And then go to another node which depends on T2, T3. So that is T1. So that is why it is T2 to T3. So it's a standard topological sort. You can look at graph theoretical algorithms or data structure books if you want to know a little more formally about that. Now, a select operation, I have questions. The algorithms are simple selection operations. Now, in selection operation, actually, you have to remember the physical storage of the file. The file is stored in terms of a particular sorted order of on some column the file is sorted physically. Physically, file is sorted in a particular order. primary key is typically that order. Of course, you can change it by indexing on and things like that. But in general, primary key is the one and which is the most efficient one. So if you want to see whether this condition is matching in your relation, what you need to do? You need to find out all the records of the relation. Where are the records placed? Records are placed in blocks, right? And the beginning of the block address is known to us. And the blocks are contiguous. It's a sequential file. Blocks are contiguous. So what I need to do, I need to go to the first block. How do I go? I seek. It's in a disk. I need to seek. By seek, I mean I need to go to the particular disk, and then in that particular disk, I need to go to the particular track. And then in the track, I need to go to the particular block. That's seek. Now there may be BR number of blocks. So I need to transfer all BR blocks in my memory so that I can check whether this condition is met or not. Now, if you say that it is a key attribute, then on the average, I need not look all the blocks. Why? Whenever I get, if this SSN is present in some particular block, in some particular record in a particular block, I need not go to other blocks. Why should I go? Because I have got it. And it's a primary key, it cannot be repeated. So there is no point in going there. So at the minimum, I need to transfer one block. At the maximum, I need to transfer all blocks. So on the average, I need to transfer half the blocks. That's the basic philosophy. Now, binary search you can involve, no doubt about it, but binary search can only be done if it is an equality comparison. It cannot be done on non-equality comparisons. And then it has a number of overhead, like seek will be more and things like that. Now, if you have a complex query like this, and this query is not on primary key attributes, then this is a time-consuming query. You have to check this query for every record in every block, right? Binary search will not be able to help you there. And there are so many different other methods. You need to tell me which method you cannot understand in detail, and then I'll get back to you with explanations. We'll do that. So we almost have come to the last. So I think we have some questions on the rollback. Rollback. You have some questions. So look at this particular transactions. You see, this transaction does not commit anything, and then all of a sudden it aborts, right? So this write on this write, this read is dependent. So therefore, you can say transaction 11 is dependent on T10. If T10 aborts, then T11 becomes very useless, because the value in T10 is not understood and not really preserved very well. So similarly, if T11 writes and T12 reads, then on T11, T12 depends. So therefore, if T10 aborts, then you need to roll back the entire thing of T10, and not only that, T11 and T12, because they are kind of linked in a sense. So that's what I've written here. So that's called cascading rollback. And the interesting part is, if it would be a commit here, right? Even after commit, if there is an abort, they are already permanently placed in the database, right? So this read has read from the database, in a very correctly. So this, after this commit, if it is aborts, then these lines in T11 has no problem. Similarly, if T11 commits and then T12 reads, even if T11 aborts, or T10 has a problem for T11 has a problem for T10, that problem does not touch T12. So cascading effect of this abort does not take place. Cascading does not happen in case of this. If you take such precautions. So this is called cascadeless schedule, right? I think there are some other questions which are about. One question is sample model questions. It is for the admin to answer. we cannot provide you model sample questions in any form. I can give you many, many write-ups, many things to read like that, but I cannot really say that it is a model question. I can even give you some assignments if you want, but I cannot give you model questions like that. I mean, that's not permitted under the jurisdiction of ours. And the questions are all whatever you encounter. I mean, the type is not descriptive, no doubt, but MCQ, MSQ, these are the two types that you will find out as you are finding them in your assignments. As far as I know, it's an online exam, but it's not from your home. It's online exam where you have to go to a center and give your exams. But this question will be answered in forum. I'll take this question because I will ask the admin about the methodology that they. I mean, I want to ensure the answer, and then I'll give you that answer after I do that. So I'll ask my. I mean, I'll take care of that, and I'll give an answer to the announcement kind of a thing in the forum. No doubt, no problem about that. In any case, these circulars are given to the students from time to time by NPTEL admin as well. So don't worry about that. And I guess that's the last thing. Is, I mean, it does not have any question. It says that sometimes I have said that you need not know this detail, or sometimes I have said that. I mean, even Professor Das in his lectures might also say that. If we do not give an answer, that means basically you do not need that for this particular course. But of course, you can ask any one of us for clarification, further clarification, supplementary readings, and things like that. We'll be happy to do that. Now, there is a live dashboard. I guess there is a question that has come: how to write SQL query. Now, how to write SQL query was actually taught in, I think, more than one module. I mean, there are 2-3 modules in which we tried to explain. Professor Das has tried to explain how to write SQL queries. We have tried to give you a number of examples, and also have given you the tools in which you can run your own SQL queries. So you need to take them up, and if you want to read something and things like that, you can ask us. So with this, I think that's the end of it. I have no more slides, and therefore I complete this session at this point of time. Thank you very much for your patient hearing, and I hope that those who could not attend will also look at this video for clarifications if they wanted to have. Thank you so much, and